Okay, so before we get going today, I am going to go back a bit to section 2.5. And when we're talking about the phase lines and the autonomous equations. I had mentioned then, so our function is dy dt is some rate 1 minus y over k y, and that's some function of y. So I said that the book did not necessarily describe how to get your graph of y versus t or f of y versus y. That's actually not right. They do describe it, just not in that section. So if you would graph y versus t, this over here is exactly what we did in the beginning with our direction fields or slope fields or vector fields, whatever you want to call them, that we can pick certain y values and then we can get the slope and then we can draw that direction field. So for example, if we pick our y value to be k, our whole equation becomes 0. So we'll have slopes of all 0 there, which is what we saw. Same thing with 0. We have slopes of all 0. If you pick a value that's bigger than k, then this thing will be bigger than 1. And 1 minus something bigger than 1 will be negative. So when we're up here above k, we will have negative slopes. And if it's a value close to k, it's going to be a fairly shallow one. Getting farther away from k gives you a steeper one. And so from here, we still end up with our general line that's going to look like that, kind of an exponential type thing. Now, if we pick numbers that are y values close to 0, it's going to be a fairly shallow number. If we pick values close to k but are smaller than k, again, we get shallow values, but they are all positive. If we pick numbers that are more in the middle, around k over 2, they are going to be steeper values. And then we could fill this in for a whole bunch more k values in there, or excuse me, y values. But then again, you still get the general idea. So you can draw these graphs just from the equation. And as we saw before, if we're going to do our function, our graph of y versus f of y, we can find our intercepts. If we multiply everything out with this, we'll get our y squared. That's negative. So it's a parabola opening down. And so we can get our graph drawn. And then based on what we know about our graph on the left, we can then draw our phase line from there. And then we find our asymptotically stable solutions, our unstable equilibrium solutions, and go from there. One other thing that is mentioned in the homework, but we didn't cover it in class, is we can have more than one of these. And you could get a situation like this, where these solutions are flowing into K2 or K1, but then they're flowing out of K1 down to K2, and then these ones will have come up. So up here, K1, since some things come in, some things go out, is called semi-stable. K2, since everything is flowing in, that would be our asymptotically stable. And then down here at 0, since everything is just flowing away from it and it's only one thing that's going to stay there, that is our unstable equilibrium. And then I would say there are two thresholds here. One threshold, I can spell threshold, is at y equals 0. Because at 0, it stays there, and above that, it goes up to K2. I would also say we have another threshold up here at K1. Because above it, it goes to K1. Below it, it goes to K2. So you have some dividing line there. So two thresholds and a couple of different ideas here. So further emphasis on the asymptotically stable. If you have multiple things flowing to it, multiple starting points are going to go to that line, then it's going to be somewhat stable, either the semi-stable or asymptotically stable. If only one thing is going to go to it, that's when you're going to get your unstable solution. And you can't have more than one asymptotically stable. So for example, let's go K1, K2, K3. So those are all where we have critical points on our equation. So this is asymptotically stable equilibrium. K3 will also be an asymptotically stable equilibrium because we have multiple things flowing to it. This one at K2 is unstable equilibrium solution. And also down here at 0, unstable equilibrium solution because only one thing goes to it. This would also be a threshold because that's our dividing line. Above it or below it decides where you go to K1 or K3. And I would also consider that a threshold. So there's your little bit of review and further explanation. Let's go on to the main topics we want to discuss today. So they changed some of the book, and the notes I had written for 2.9 are not what the book has anymore. So I'm still going to present my notes, and this will be a nice way of solving some of these more complicated differential equations. So if we have some second orders, and this will kind of tie into what we're going to do in 3.1 as well. The general setup is y double prime is going to be equal to some function of x, y, and y prime. However, we don't always have all of x, y, and y prime. Sometimes we're missing one or more than one. So we're going to look at two situations. One, what happens when we're missing y? So in this case, we are left with y double prime is equal to a function of x and y prime. Now for here, it's really easy what we want to do. We can just say that introduce a new variable, v is equal to y prime. So then v prime is equal to y double prime. So our new function becomes v prime is equal to a function of x and v. And we've now taken a second order equation and rewritten it as a first order equation. And we already know how to solve those. We can do separable, we can do integrating factor, a couple ideas. Now, the issue is though, whenever we solve this, we will be solving for v, not y. So we will have to do a little bit of extra work. Once we find y, or excuse me, once we find v, it's going to be in terms of x. We then have to remember that that is y prime. So we will have to take a second integral to actually go ahead and solve for our y. So there's extra steps involved, but it's a way to take a second order equation we normally don't know how to do and solve it. Next setup. What happens if we're missing the x? Well, then we have y double prime is equal to a function of just y and y prime. So we're going to do the exact same thing, just different. We're going to say our v is equal to y prime. Problem is that in this equation, we're now going to introduce these v primes and y's. So we want our v prime to be in terms of y, a derivative with respect to y. What we have so far is y prime is with respect to x's. It's a dy dx. So we do need to make a little bit of a change here. So whenever we do our v prime, that is going to be the same as our y double prime. But the problem is that our v prime is dv dx, not in terms of y. So we have to do a little bit of a change. We're still going to have that dv dx, but we're going to multiply it by, well, we're going to split that up actually. We're going to make it a dv dy times dy dx. Now we can't just simplify this and make it the same, but if we use differentials, then the dy's would cancel and get back to where we started from. So this is all legal to do. Now, dy dx is a y prime, which is the same as v. So this is really v times dv dy. So our new equation is a v prime equals f of y and v, but it's v y equals a function of y and v. And then we can easily just get this to be dv dy equals our function of y and v divided by v. So it's still functions of f, or excuse me, our dv dy is still a function of y's and v's, even though we're dividing that v over. And we can still treat it like a first order. But now we will have we're going to be solving v in terms of y. So then that's really becoming, once we have v equals something, that is really y prime equals something, but it's a something with y's in it. So now we will have another equation to solve, but it's going to be a first order equation that we now have y primes with y's, and we know how to do that. And so then we can go ahead and solve it for y. So again, 2 times we have to do this, but we can reduce it from a second order down to a first order and then solve it like we normally would. Well, first we reduce it to a first order, solve it, which is a new first order, and then we solve. So there's our general idea of how to approach some of these equations or some of these different situations that are second order. Last thoughts on this. The nice thing is that no matter what you're doing, your main change is y prime equals v. And then your v prime is going to equal a y double prime. Thing is, here we have x's, so you can keep it the same. Have your derivative in terms of x, so you're fine. Down here, you have to get in terms of your y's, so you have this little bit of a change, which is your v times dv dy. So a little bit of a change in there, although it's not too different from whenever we had the other stuff with the homogeneous thing and factoring out your x and making v equal dy or y over x and then doing your derivative in the product rule. So it's the same type of idea of a change. Now let's move on to the main thing for today. We're going to talk about in section 3.1 second order linear equations. So before we do that though, we're getting into some very special ones. Our second order linears. General setup is going to look kind of like this. P of t times the y double prime q of t times y prime plus r of t times y equals g of t. If we have something that's nonlinear, then one of these, at least one of these y terms, will have an exponent that's not just one. When we talk about homogeneous, or homogeneous, take your pick, that's when our g of t is equal to 0. If we have non-homogeneous, then our g of t is not equal to 0. We'll make that not equal. So our focus is going to be second order linear homogeneous with constant coefficients. So there's a mouthful for you. Let's break it down bit by bit. So second order. So that means we're going to have a y double prime somewhere in there. Linear. All of the y terms are going to be to the first power. So that's nice. Homogeneous. Our g of t over here is going to be equal to 0. So that's going to simplify things a bit. In constant coefficients, that means that our P, our Q, and our R will just be numbers. We don't have to worry about T's being thrown in there. So this is really going to simplify things a bit. When we do all of this, our equation simplifies. Oops, some number times a double prime, or times y double prime, plus b times y prime plus cy equals 0. So that's going to be our general form that we're going to get. So let's look at an example. So y double prime minus y equals 0. We've looked at one of these before, and we'll see about working through all this stuff later on. But for now, we know that in e to the t, or e to the negative t would both work and satisfy this solution. You go and take your derivatives and go from there. So possible solutions we could have a y1 that's some c value e to the t. The other one, y sub 2 of t, is c2 e to the negative t. So those are the two possible solutions individually. Now our general solution could have a combination of these. So we could say that our y, and it's going to be a y of t, is equal to our first solution plus our second solution. And if we had any combination of an e, something times e to the t and something times, or plus or minus, something times e to the negative t, then it would still work out that our overall solution, our overall equation would be satisfied. And so if you just do a quick check, if you do a y prime, you get c1 e to the t minus c2 e to the negative t, and then a y double prime, c1 e to the t, but now it's back to plus c2 e to the negative t. So looking at your y and your y double prime, they're exactly the same. So if you subtract, you get 0. All right, so we can have confidence that that works. Now, what we're going to say is that we will have a fundamental set or a fundamental solution set, if you want. And that fundamental solution set will include, and we're going to write it in set notation. You write it as a group with curly brackets, that we have those two involved. Now, in order to find, so it's going to be some combination, linear combination of these two. And we can multiply some numbers in front, and we're not sure. But here's the main functions that we're dealing with. And now if you wanted to find your C1 and C2, you would need two different initial conditions. So you'd have to know what happens when your with your y at some t naught and your y prime at some t naught. Or you would need to know what is y at a certain value or y at a certain other value, like about, and we call those boundary problems. So, but anyway, fundamental solution set is going to come down to these. Okay. So let's look at how we're going to do this in a more general sense. So let's go back to our general equation of a y double prime plus b y prime plus c y equals 0. So from here, we know that a possible solution is y equals e to the RT. So that would make our y prime r e to the RT, and our y double prime is r squared e to the RT. Or they could be to the negative t as well. So, but let's just start on this. Now, if we do this and we substitute this into the equation, it's a r squared e to the RT. plus b, and then our y prime, r e to the rt, plus c e the rt equals 0. Now notice what they all have in common. They all have this e to the rt. So therefore, let's factor that out. And we're left with a r squared plus b r plus c equals 0. This e to the rt is never going to equal 0. So it's never going to contribute to our solutions. The only thing that we're left with that we have to worry about is this little bit in here. So when we have these second order linear equations that are homogeneous and constant coefficients, we can just treat all of it like a quadratic, which is going to make life a whole heck of a lot easier. And now this thing in here, this AR squared plus BR plus C, is called our characteristic equation. So we're going to focus on that characteristic equation. We're not sure, so they're going to give us certain A's, certain B's, and certain C's in our equation to solve, back up in here. We'll then change it into the characteristic equation and focus on finding the R values that'll make this true. So when we're done, we're going to find some certain R1 and R2 that are going to work. Potentially two of them. We know with quadratics, we could have no solution. We could have one solution that's repeated. We could have two individual solutions. Well, no real solutions. There could be two of them. Then we could have one repeated real, or we could have two real. So idealized version is whenever we get our two different solutions, R1 and R2, and either from quadratic or factoring if it's easy enough. But now we are going to have our Y1 is going to be C1 e to the R1t. Our Y2 is going to be C2 e the R2t. Those are the individual solutions. Overall, we're going to do what we did before. And we will make a linear combination of R2 to get a general solution. And of course, that's if our R1 and R2 are both real numbers and they are distinct. So then whenever we talk about our fundamental solution set, that's going to be fundamental set. And why do we worry about our fundamental solution set? Because it is fun. I knew that joke was coming, right? Okay, so let's actually look at an example here. And let's see how we would solve it. So let's do two of these, two examples. We'll do one that's just general. So we won't have to necessarily find our C's for this one. We have y double prime plus 3y prime plus 2y equals 0. So writing this as our characteristic equation, we're down to there. And then this one can be factored fairly nicely. So therefore, R is going to equal -1 or -2. So whenever we go to write our solution, e to the -t, and then our y2 is e to the -2t. Now, it really does not matter which one is y1, which one's y2. They're interchangeable. So our overall solution now, for the general solution, is there. And if you go ahead and find your first derivative and your second derivative, then you can plug it in and you will see that these things do indeed work out. And your first derivative, you will get your different numbers up front will be negative. And so they kind of will counteract and balance here. And then with your 3's and the 2's and everything works out the way you want it to. Let's do another one. Although if you really want to, go ahead and take your derivatives and plug it into the equation and you'll see the nice relationship. This one says y double prime plus y prime minus 2y equals 0. But we're also going to say that y of 0 is going to equal 1, and y prime at 0 is going to equal also 1. So let's go about doing our business. Change to the characteristic equation. We can factor. So we know that R is going to equal a -2 or a 1. So individual solutions. And if you wanted to look at your fundamental solution set, we have it there. And then overall general solution. All right, but we still have to find our C1 and C2. So now we have to go back to our original setup. And let's find our derivative. Oops, this one should be C1 over here. Okay, but now let's look at our initial condition. We made our t's all equal 0. Our y value was a 1, and C1 times 1 plus C2 again times 1. Looking at your derivative, we're there. So now we solve the system of equations. Probably the easiest way is elimination. Go ahead and multiply this bottom one by a negative and then add together. So 0 equals 3C1. So C1 equals 0, and that makes C2 have to equal 1. So our final real answer for this, with these initial conditions, is just e to the t. Let's actually try one more. Let's try to see if we can get one that's a little bit more satisfying result. Okay, fundamental solution, or excuse me, our characteristic equation. So we end up with that looks a little bit better, like an actual 1. Fundamental solution set. Now you don't need to write all of this all the time. I'm going through it just so you have repetition of words and you're connecting ideas, because you never know what the question is going to ask for. Overall solution. And you don't need to use C1s and C2s. You could use 2 different variables if you'd like. This is just a standard convention. Just make sure that they are different values. All right, so let's do our initial conditions on this. Whenever our t is equal to 0, that is a 2. And then the e's are no longer a concern. That's a -1. So right off the bat, we have things that are set up nicely for elimination. That's a 1, that's a 2, C2. So C2 equals 1/2. Using our top equation, we can see that our C1 is going to be 3/2. So our overall equation for this is 3/2 e to the -t plus 1/2 e to the -3t. So it's a fairly straightforward process. I'm going to make that a little bit nicer on the bottom there. As long as you can do factoring or the quadratic, and then you can solve systems of equations, it's not too bad of a process. So that is it. Enjoy your couple days without seeing me, and we'll see you on Friday. You have a couple of, well, 3 quizzes due, 6, 6.5, and 7.